I think we've allowed an hour for this presentation. We shouldn't take that long, so there should be time at the end for questions. I'm going to try to progress my screen here. Hopefully everyone can see it. Yell at me on the inside if we don't have a change. So let me lead off with who I intend this presentation for, this solving important sanitary sewer problems. So this is for you if, and I'll list a few bullets here. So if you've never modeled a sanitary system, you should still be able to get something out of this presentation. Hopefully you're familiar with the systems, but if you haven't sat down and modeled them, you'll get something out of this. If you've never used XP Swim, that's totally fine. What we'll talk about, you'll see some XP Swim screen captures, but it's really agnostic to the software. We're trying to be a little more high level than that. But if you've done modeling before, I still hope you'll get something out of this. Perhaps you've had trouble vocalizing some of the modeling needs, so some data needs and some other needs. You'll still get some value. And perhaps this is an important one that I found. You have trouble conveying modeling requirements, so the requirements of to build a really fruitful model. And finally, if you've been able to jump over those hurdles in your career, if you're interested in extending some applications, you should still be able to get something out of this presentation. And so I should note, I am trying to balance theory with practice. I am a theoretical person by nature, but I want to be practical. That being said, if you haven't joined us in one of these webinars before, this isn't a tutorial. Again, we're not going to jump through exactly how to do this in XP Swim. So it also isn't training or support. So we're a little bit abstracted above that when we talk. So with that being said, let's show you kind of a roadmap of what we're going to do. I want to start a little bit with some history. So that's my theory side creeping in. But then I'm going to get into the four problems: growth, optimization, regulation, and maintenance, like Nicole mentioned. We'll talk about the problems as well as hopefully what you're here for, more of the solutions, modeling solutions. Another caveat I should mention here is that models are a tool and they're important, but they're not just a solution. So I like to mention that, especially for people who find models to be a black box. We use those as an important part of the solution, but they're not in and of themselves a standalone solution. So bear that in mind when we get through what we're going to cover. So let me start a little bit with the background, and this is framed more in the U.S. And so this blue line is a timeline. And so we'll start way back, and actually it predates this a little bit, but we'll start back in the 1600s. So actually was some rudimentary sanitary systems in the 1600s, basically hollowed out logs directly to creeks, but that existed. You can find it all the way back there. And existed for some time. Even as early as the 1700s, we had collection systems, and they were not well designed. Sometimes they had no slope, and they might be miles long, but they were actually collection systems themselves. Understanding that a bunch of hollowed out logs isn't as good as one trunk system. You can see in the 1850s the advent of some steam-powered pumping systems. What you see in that picture is a quite large raw water system, but they existed in the sanitary world as well. Another big thing that is more pertinent to what we're talking about today is the larger growth of master planning after the Second World War and getting into master plan communities and seeing more master plan studies of trying to have a little bit better of an idea of a planned growth, and all the way through today. And we've seen additional increases in complexity of master planning and other things, but those are kind of the main backgrounds of sewer. So what if we take that and think about it in the context of the modeling background? Well, I have the same time frame here, but obviously modeling, even though it's been around for some time, is much more compressed. In fact, if I were to show you the modeling background superimposed on the sanitary background, it would be about that size, much smaller. But it is bigger than I think a lot of people are thinking, and it extends back further. So we'll go back to the beginning of modeling from the standpoint of sanitary sewer. Certainly mainframe computers and other things existed before the 1970s. But you see the first personal computer credited in the 70s, as well as the Swim 1 engine, kind of the backbone of most modeling platforms, whether that's XP Swim, EPA Swim, or others. That progressed in the 80s. You'll see new versions of the Swim engine developing in the 80s. And then we get into the 90s where you get arc view and office. So it's kind of a fun fact that if you have, if you yourself use a spreadsheet for sanitary sewer modeling or have a colleague that does, they're effectively using newer technology than the initial SWIM engine, even though we typically think of that in the other way. SWIM 5, which most engines are built on now or can use, is in the early 2000s. And then, of course, just like the complexity of the sanitary sewer system, the complexity of modeling itself has progressed with IBM Watson, being obviously a really powerful computer, and through and into today. So I guess to summarize that couple slides there, we've got a 40-plus year solution to a 400-plus year problem in the U.S. So what's the context of that relative to this webinar? Well, really what we're asking is how often can we solve these problems, and what really are the problems? How can we solve those intuitively and efficiently with a model? Because that's the goal. We're not really trying to find a solution and hunt around for a problem. We really want to find the problems that make a lot of sense. And so that's really what we're trying to do. So let's go ahead and get started and find out with the first problem, which we framed as the growth problem. And I'll start with a little bit of a backstory. I have a great book from the mid-50s called More Water for Texas, and I scanned these pages directly out of the book. And so there is one of the plates in there is the United States population from 1790 to 1950. If you notice, this is from 1954. Here's what that plate looks like. And the reason I bring this up in the context of growth is there's a line there for 1950, and then there's a projected line to the year 2000. So we have a roughly 50-year projection of population. And so I wanted to check that. So in 1950, roughly, the estimated population is 227 million of the U.S. And if you check the actual census population, it was 284.1. So a 24% difference, which if you were to ask me, I would rate that at maybe an A+, maybe an A. That's a pretty good guess, because as soon as you make an estimate of growth or an estimate of flow, it becomes old. And the further out you project that, the older it gets. So maybe a more practical way to state that problem is, how can a model, any model, predict changes to flow? Well, it can't really predict changes, but it can adapt and respond to those changes. And there are some ways that are more practical than others to do that. So let's cover those solutions. And I like to say that's important like paying taxes. And by that I mean it's not necessarily the most fun to do all this work, but this is really the most straightforward way to do it. So I'll have some big words here, apologize for that, but the best way I can describe it. And the first is parameterization. And by that I mean we're going to break down what we mean by flow, and we'll start with dry weather flow, what we mean by flow into building blocks that we can make physical sense out of. So here's an example of a dry weather flow interface. And I'll alert you to a few things here. In this instance, we're calling this a census-based dry weather flow. And you can see the flow rate is made up by a normalized flow rate. So this could be a per capita flow rate. So let's say 110 gallons per day times an area, times a density, times a peaking factor, and then times a variation. So there's lots of multipliers there, but you've seen that we've broken it out into individual parameters. And that's really important. If we have those individual parameters, we can break apart any of the characteristics, again, physical characteristics of the system. So let's say we have a GIS system and we have sewer basins that may be disaggregated based on land use. So perhaps I have a residential, a commercial, and industrial land uses. Well, those may have their own patterns, their own densities, their own peaking factors, their own flow rates. If I can break those up, then I have an exact idea of where the flow came from. So it's not just, let's say, 1 million gallons per day. It's based on a real population and a real density. So why is that important? Well, it's important for two main reasons. One, it's a lot easier to justify the flows when you can tie it back to something physical than to just, let's say, a meter. The second is it's easier to relate them. And what do I mean by that? Well, there are two ways. One, if you have the ability to have different scenarios, I can start, again, building into the future. So if we go back to the growth example of future growth, I may have a 2014 scenario, a 2019 to 2024. Those all have different factors. Perhaps I have a parkland that changes to residential from a land use plan in 10 years. Well, I can tie that directly into the model. I can also tie that directly into external data. Most users use something like a GIS system or other external system to track them. So if there's a different department or different group that has that data, I can store all that data and I can connect it in. So any changes externally become changes internally. And then, of course, the toughest of all for me personally, I'll only speak for myself here, is the documentation, which sometimes feels like that to me. But it's really important, especially if you're still in the mode of generating a model and then archiving it for 3 to 5 years and then dusting it off again. Having an idea of the description of where information came from or notes about how it was generated built directly into the model or into something right next to the model is really useful because things change. And the land use plan may change, the comprehensive plan may change. All those things are important. So I mentioned before, this is kind of a dry weather example. When I say growth, I'm talking about capacity. So perhaps in this stylized view, I have some amount of capacity in my pipe taken up by dry weather flow right now. And I know that I'll have growth in the future, and that will take up some capacity. But the real driver from a capacity and a sanitary standpoint is that rainfall-derived inflow and infiltration. That's really going to take up a bulk of my capacity. And a model is extremely well suited to making this kind of estimate. I almost didn't put this in because it's one of the biggest uses of a model, but I wanted to cover it just so it was all in one place. I can think of basically 3 main ways that a user of a model could estimate wet weather flows or rainfall-derived inflow and infiltration. And I'll go in order from simplest to most detailed. The first is the simplest of all, which is basically a simple peaking factor. So if I had, let's say, plant data and I knew that my wet weather flows were 5 times my dry weather flows and I had a steady state model, I might just multiply my dry weather flows by a factor of 5 to get an idea of what's happening in my system. Obviously, the advantage there is it's very easy to do that. Big disadvantage is there's no time dependence. So I have no idea of the volume of flow, and I also don't have any idea of how that flow interacts. I have no time to peak understanding of what's happening. Another way I could do that is by adding additional patterns. So even if it's a dry weather pattern, I can add it on top of my existing dry weather patterns, and now I start to have a better idea of volume and reaction based on time in the system. It's still not ideal, though, because I can't really extrapolate that. If I'm still using a design storm approach, I can't take that pattern and have it react to a specific design, or even better, if I'm doing continuous simulation, I can't extract out that pattern and see how it reacts to, say, 20 years of rainfall data. So the new standard, new is relative, but the standard that has been generally accepted is some type of RTK, which is a parameterized approach, or direct inflow. In other words, ways that have a time variance but also have an impact based on rainfall. And we could spend a whole hour just covering how to do that, and so I'm not going to do that. I'll just limit it to say that if you have the data, it's a great thing to do, and lots of different platforms will allow you to enter, let's say, RTK or interface runoff with hydraulics. I've put together a couple EPA SOAP videos. You'll see a link there that'll take you there. You can write that down. And I believe that we'll send you a link to a lot of this documentation after this webinar is over. But there are 2 videos there. The first one is only talking about EPA SOAP, and I should mention that SOAP is basically a sanitary sewer overflow analysis planning toolbox that the EPA put out. It's a free program. It's lightweight. It's easy to use. For me, there's not a whole lot of documentation, so I put together about a 45-minute video that just covers how to use the software, completely independent of any other software. It's just EPA SOAP. And then there's a second video that covers how EPA SOAP and XP Swim work together. So by all means, feel free to take a look at those, and you can get more up to speed on the RTK method. So that's kind of the first problem. It's growth, and that's a big problem. That's a big driver for a lot of modeling applications. So in other words, that's a lot of the reason that you see models being used is there's some capacity concern now or in the future, and we need the model to tell us what we're doing. There are, however, other problems. If you have rotating parts in your system, so if you have pumps, you may have an optimization problem. So on an individualized basis, that may be stated as how efficiently is everything operating in the system, and if you happen to have dozens or hundreds of these, then you might want to know on a summation level, how is my system operating on a whole? So there's the old adage of time is equal to money, and that still applies here. We'll just make a slight variation to that. So we still have the money part, we still have the time part, but in a sanitary system, when we have these rotating parts, we have the power part. I can take that kind of caricatured example and show it to you more as a formula. And so I have flow denoted as Q, H is the head, I need to lift that flow, T is how long I need to do it, and then there's usually some type of constant as well as the pump efficiency. So the pump efficiency is important. Some of the examples I'm about to show you rely on the fact that the pump needs to be efficient, and a model can help you select a more efficient pump. But we're going to concentrate on what's in the numerator, the flow, the head, and the time. So we'll break that up into factors. And so those factors have variables that affect them as well as strategies that a model can help you address. So we'll start with time, and some of these are interrelated. So I'm simplifying here to say that the wet well size or the suction size storage size is a variable for time. Obviously flow and other things are, but if we start there, we know the wet well size, so there are strategies in the storage design of that, both the depth as well as just the sheer magnitude of the wet well and its placement. Then you have head. Head varies on a lot of things, so that would be the length and the elevation, diameter, and roughness, so basically the static and dynamic head. So elevation being static, the others being a factor of your dynamic head. Consequently, there's several strategies for that. So you have the pipe design itself, which can be automated. So you have the size and lining as well as different scenarios on how you might be able to reduce the head. And finally, we have flow, which would be based on the sheer size of the sewer shed as well as the individualized characteristics. So storage, whether that's online or offline storage as well as routing, are strategies there. So those are several different strategies that can really be consolidated into just a couple. So the first being design of storage. So the design of storage is important, and there are ways to affect how long the pump runs or how high of a static head the pump has based on this. This can be used in both existing, so retrofit, as well as planning new systems. In difference to this example, screen capture from XP Swim of an actual automated optimization of the storage. So you can actually optimize it, or you can do more of a spreadsheet hand calculation to come up with the best storage method. There's also the design of the pipe. So there are ways, different platforms, including XP Swim, have ways to actually design the pipe based on certain criteria. So perhaps you don't want the pipe to surcharge within 2 feet, or you want the pipe under a dry weather condition to not be surcharged at all. You can put that in and have the computer actually solve that for you. So that's something that you can do somewhat by hand using a spreadsheet unless you get into a more complicated system. If you have a loop system or adverse slope system, it's going to be more complicated to do that. The third, and we covered this in the previous example, but it's powerful, so it applies here as well, is scenarios. Scenarios of different options, whether it be pipe design or storage design, and as well as routing. And I have my little reminder here to tell me that we'll cover routing in more detail in the next section. But just to give you an example that I've seen in the past, perhaps you have an existing lift station that's, let's say, 30 years old, and 5 years ago or 5 years from now, a relatively deep gravity line is in the area. Well, that's obviously the best increase in efficiency, is if that wet well can be tied to the gravity line and the lift station itself can be removed. That's a great routing example because that will change how the flow moves through the system and change the impacts of the system. So that's a great scenario to compare and a really good use of a model. So that's a quick overview of optimization. Again, the subset here of mechanical parts. So obviously the less often we can use that system, so if we can route to an area that's gravity, the less head we have to apply to the system, or the less power, the less dynamic head that we have to overcome, the better. The third that we want to talk about is the idea of regulations. And so I've seen growth happens a lot in models, and I've seen the idea of optimization happen kind of as a side idea of a model, if there happens to be that. A relatively easy example Regulation happens less frequently, but I still think it's important. And so what do we mean there? Well, we've seen a lot of overflows, right? This is a quite spectacular overflow, I believe, in Montreal, a combined sewer overflow. So we want to know where and the magnitude of overflows and what's causing them to happen. We also want to know, germane to this conversation, how can the collection system support that plant permitting? I'm not a permitter. This is my thought process when I see the plant permitting process. So it's complex. It has a lot of moving parts, but there is a efficient role that a collection system model can play in that permitting. And I'll show you what I mean by that. Well, there's two tracks that can happen. So the first is living directly in the collection system, and that's an overflow. So overflows are a problem no matter what, but if you have enough overflows, you might have a consent decree or some other type of legislation or otherwise that is going to greatly quicken your response to planning. A lot of times that happens through the CMOM, and that's an acronym, Capacity Management, Operation, and Maintenance. So basically a fairly holistic way to manage your collection system. And so a model can help with that. CMOM itself can cost some money. Continued problems with your overflows can cost more money. But there's a parallel track here as well. And we'll step all the way back to the Clean Water Act and say that we need to make sure that our impacted water bodies aren't getting too many nutrients discharged to them. And so over time, as new permits come out, that can have a direct impact by the necessity of upgrading a plant. So for instance, I know enough to know that very low phosphorus limits require tertiary treatment, which is expensive. And I've seen over time new permits come out that lower that limit on an impacted body of water, and that can have a real cost to implement. In addition, on the plant side of things, you can have local, state, or other regulations that say that once you reach a certain % capacity, you need to start planning or constructing your new plant. And that's usually on a permitted capacity, so it may be a sheerly larger plant, or you may have, again, different treatment standards, which is expensive as a CMOM is to implement. This is much more expensive, and so it really helps the planners to try to come up with ways to offset or delay this or eliminate it if at all possible. So we'll start with the CMOM as far as our solution on the regulation side of things. Well, CMOM typically will have an inventory required, and if you don't already have an inventory as part of a GIS or other system, your model will give that to you, which is really nice. So you can export that out in whatever tabular format you need, but you will have an inventory of your collection system. Also, kind of as a side note to your model, you will have mapping. So it may be in a GIS system or not, but you'll have mapping, which is helpful, and you'll have capacity assessments. That's kind of the bread and butter and the purpose of having the model, to give you capacity assessments. Specifically on the overflow side of things, you should be able to get a magnitude, location, and frequency, which is something that the CMOM wants, as well as some response planning. I'll give you a couple screen captures, just some basic examples here. You can see this node. It's a little hard to see. Apologize for that, but you can highlight. On the right side, you have a volume, a cumulative volume of overflow, as well as when this happened. So this is showing you that this node that you had 20,000 gallons that began to overflow at 3 o'clock in the morning. That's for an individual node. If you had a problem of a lot of different nodes overflowing under a certain scenario, you could see that in a more tabular way. So again, the time, the duration, the max volume, and those are things that typically have some link to GIS. You can extract that data out, and you can do further processing with it. So really helpful if and when, hopefully you don't have to, but if you have to be under any kind of CMOM, or you're just developing something like that to have a better overall management, then the model certainly will help you there. So the other side of things is on this nutrient removal and capacity reach. And those are two related things that I'm going to join and call one thing. I'm going to call that routing. So we talked before on optimization about routing. So I'll give you a more thought out example here on the regulations. So we'll start with a very, very basic example. So we'll assume we have two water bodies. They're denoted by the blue lines pointing down, and some type of dividing line between the two. So that's the orange line there. So let's assume that we have two treatment plants. Because of the natural grade change, we have a plant A and a plant B, and they're discharging into water stream A, water stream B. Well, as can happen, we might have different limits of criteria nutrients on these two. So let's make the assumption that water body A has a less stringent nutrient limit, and water body B is more impaired. So it's the SAD, impaired water body. So what can we do here? Well, typically we'll have industrial pretreatment, but you still may have a certain quality of flow that you might want to move. And so a model with routing and scenarios is good at telling you a certain area that might naturally drain in B, and maybe some way to drain it to A. That's less common, although it's possible. More common is the quantity. So perhaps there's a larger area or just a different area that would naturally flow to B that I can move to A. Perhaps it's 10% of the capacity. And if my plant A can handle that capacity, and I can move it from one to the other with a few different size pipes or a different configuration of a force main or some different variation of my hydraulics, then I can really assist on the permitting level. And that may delay a $50 million expansion for 15 years, 20 years, which is a real value to whoever owns and operates that system. The final thing I wanted to cover is maintenance. And this is honestly becoming one of my more favorite things to cover because I love hydraulic models and I really enjoy there being practical reasons to use them. So the first three we talked about, growth, optimization, and regulation, are important. They don't change that often. In other words, it's not like every month you have a new reason to optimize your system. That just doesn't change that often. But maintenance, as we're aware, is an ongoing thing. And for a long time there really wasn't data or reason to use a model to support maintenance. And I'm believing more and more that that's becoming more practical. So what do I mean when I talk about maintenance? Well, one is where are areas where settling might occur. So if I have a siphon or if I have an adverse slope or a zero slope, I might have a settling or other problems occurring. And a model can help us determine where that is. Perhaps we have a generation of soaps or oils or greases as well as roots. Where might that be occurring, and can a model help me pinpoint that and solve that? And the third is where are there any areas of odor or corrosion? So where are those? So those are the big three in my mind of maintenance. And so again, trying to be practical here, is there an operational change? Is there something the model can do that can affect these areas? Because if so, we should explore that more. So let's go individually. The first being settling. So you can find some information on settling. This is not the newest one out there, but this is a good EPA guidance document on characteristics of sanitary wastewaters. Obviously, ideal if you can collect some information on your own system, but there's some information out there. Well, how could we use that? Well, in my professional history, the gold standard is 2 feet per second. So what you see here is several different variables on one screen. So this is a pipe. You can see the downstream and upstream elevation as well as flow and velocity. So in this instance, the red dash line is velocity, and I've drawn this blue line straight across at 2 feet per second. So it's kind of a rule of thumb that if you're in the 2 feet per second range, then you might be beginning to settle. Well, if we look here over the course of 4 days, every day we get close. We're 10% above 2 feet per second. So is that a problem or not? Well, we also get much higher, right? We get close to 3 feet per second. So is the 3 feet per second enough to wash away anything that the almost 2 feet per second generates? Well, if you just have a spreadsheet or just kind of have an idea, then you can make an estimate, or you can pull a manhole and see what it looks like. You can also actually model that. And so this is an example of taking that same size distribution you saw in the EPA document, putting it in the model, and actually running it, and actually depositing and resuspending the solids in the actual model. So whatever flow actually occurs, and hopefully you've done your homework and you've disaggregated it and parameterized it so you have a really good idea of the flow, you can actually see what happens over time. So that area that's maybe a 0.5% slope, you can see what happens. If we do some routing and move the flow so there's less flow there, now maybe the velocity gets even lower, now maybe we have problems. Or perhaps you're routing a sludge return line, something that might have a higher than average solids percent. That's something that you can model and get an answer on more than just the rule of thumb answer or the estimate answer. That's one idea of maintenance. So the other is the acronym FOG or FROG, and it's just whether you like your roots or not. So fats, roots, oil, and greases. So I like to think about this as just extending a hydraulic model. So the hydraulic model should be really good at providing you hydraulic results. That's kind of obvious. If I take an example of roots and I take a well-calibrated model that's extrapolating out my good flow metering data into problems throughout the system, I have an idea of where I&I may occur. I can take that and export it out and start using GIS. So here's an example of what I would say is a typical, you see some housing, you see some light commercial, maybe a little industrial there. And you also see a lot of tree cover. And so in this instance, it's actually been digitized out, so I can remove that and just see the magnitude of the tree cover. Why do I mention that? Well, in this same area, we have a trunk line with the collector lines. So you see the blue trunk line with the red collector lines. And if I apply those back, you can begin to see that the trunk line has a lot more root cover than the red collector lines. And you can kind of see that a little bit better here. So if I take my hydraulic results and see that there is a lot more infiltration or maybe some inflow based on the trunk line, and I compare it to this tree canopy, I can see areas where root intrusion may occur. Again, at the very beginning I mentioned that the hydraulic model isn't the solution, so that's not going to solve your problem, but if you're a big system that maybe is only inspecting 15% per year of your system, or if you're a small system and just don't have the funds to own and operate a CCTV, it's a great way to be able to detect areas and start specifying potential solutions based on the exact problem. And there again, you can see the line that has the most tree cover on it. The final thing I wanted to cover on the idea of maintenance is odor and corrosion, which are related. So, and I should say for any of those, and I spent a couple years in grad school of my life up to my nose doing this, so I'm going to greatly simplify this for the purpose of a webinar. There are two main requirements here. So we need to have some source, both for odor and corrosion, and then for the odor we need some kind of conveyance. So we need to be able to get that from the source to a receptor, which could be a person or a building. So we'll concentrate on those two things, those requirements, and we'll start with conveyance. So you can relate the airflow to the water flow in a pipe, and that makes some intuitive sense to me at least. So as water is flowing down a gravity pipe, it is dragging air with it, and there is a relationship between the amount of water going down the pipe as well as the amount of air. If you have grade changes, you're going to have a change in pressure, and you can potentially be either drawing air in or pushing air out of your system, especially if there are holes or cracks or designed vents in your system. Those two things will give you a conveyance method. And then you're going to have a source, so the source can happen from a number of different ways, but a long travel time is really good at generating anaerobic conditions, which is something that hydrogen sulfide likes. You can strip that out and get it out quite efficiently with turbulent points, whether that's a major grade change or a drop structure, something like this. And then, of course, the quality itself, which is something that you can model, or you can just do some sampling to determine the quality. So you may ask yourself, given all these different things, why are we talking about that in the context of a hydraulic model? Well, that's because a hydraulic model can predict pretty much all of those things. If you think about it, the geometry of the model would tell you any drop structure, change in grade. You can calculate travel time based on the flow, the velocity, and the length. And if you know the relationship between air and water flow, you can calculate that as well. And I built something that actually has that all as part of database triggers, that will actually calculate that based on just results data. So just hydraulic results data and the topology of the network, you can become a little more aware of where these problems may exist. And I think that's really important. Again, not to know exactly every single time, but you have a good idea. And we're beginning to see more and more real-time data, a lot more flow monitoring and rainfall monitoring, both in the duration, permanent installations, as well as the frequency. And we'll cover that again in just a minute. But I wanted to cover, in addition to those four we just talked about, we're still talking about it just within the context of a model. This is a document that is a few years old now. You can download. It's jointly partnered with the American Public Works Association, American Society of Civil Engineers, North American Clean Water Agency, and Water Environment Federation. So 4 really big players in the area. And it's titled The Core Attributes of Effectively Managed Wastewater Collection Systems. It's almost like even more holistic than CMOM and not necessarily quite so under quite the same conditions. So it's just what are the attributes of people who manage a system well. And there are 12 of them. One of them is that they have a computer simulation, which is kind of self-serving for me to say because I like computer simulations. So one of those 12 elements is that. And there are sub-elements to those. So obviously we've just talked about that. But look at all these other elements that are part of an effectively managed wastewater collection system that are kind of built in as part of a sanitary sewer model. You typically will have flow monitoring and you'll have some I&I assessment because that generally drives the capacity. That will require some type of field investigation, and it's a great opportunity to refine those processes. There are usually performance measures that are built in to help define solutions. There's some type of documentation, especially if you're doing a good job with your documentation. You can do overflow response planning because you'll know when, where, and how often, and you can even begin to build a framework for getting some of the data that we all know we don't get when we do the project for the next time. So it's really a great, to me, it's a great validation of how well a model can play in as part of a solution to managing a collection system. Let me conclude a few more slides here. So I wanted to say sanitary systems are more complex, but that's not really true, right? They're 400-ish years old. They're certainly 100 years, 50 years old. We've had pumps for 150 years. They're maybe not more complex, but they do have more data. Data is coming more and more. And kind of, I think in a related sense, stakeholders, whoever they are, whether they're operators of the system or users of the system, are expecting accelerated responses, whether that's from odor or maintenance or rates. They want to know why the CIP costs this much money. And it's really effective to have these key performance indicators built right into the model, tied directly into data that's already been approved. It's a really great response when you have a significant CIP budget, which, let's face it, the CIP budgets aren't going down as the pipes get older. I believe that these models can solve these important problems, not just these individualized problems, but they really provide value throughout the whole process. And again, that's kind of a cliched theoretical, and I don't like to be overly theoretical, so we have taken this. This is a link you can go to. You can write that down, and what you can do is download a copy of XP Viewer, which is a free piece of software you can download. You don't have to register, and you just download it, and you can view a model, and this is kind of what the model looks like, and it's purposely simplistic. In fact, while it may look a little more complex there, that's the base map. So a nice simplified model. But what's nice about this model is it covers every one of the things we just talked about. So it covers how to disaggregate and parameterize growth. It covers how to optimize. It covers how to route. It covers scenarios. It covers maintenance. It covers all of those things. So you can see what we mean, or what I mean when I say that. It also comes with its own documentation. So it's kind of a follow along, so you can see where in the model when we say growth, what we mean by that. So you can follow along and see, and perhaps you can extend it. I'm always open to people coming up with new and creative ways and logical ways to make the model do more. So I'll leave the link up there for just another minute, but if you copy that, it's a zip file, so you can unzip that, download XP Viewer, and off you go. And I'd love to hear back from you with any questions or concerns you have based on that. That's all I have officially here. I think we're at about 45 minutes, which is about what I was hoping for. Didn't want to push it too close to an hour. There's my contact information. I am the product manager for sewer products for XP, so I have interest in that both from XP's software line as well as just general interest in it. So I mean it when I say it, and some of you have smartly taken me up on it. If you have questions or feedback or concerns or just want to talk about it, my inbox is always open. Just reiterate, I appreciate everyone's time, and I hope to talk to you all into the future.